Salam, doctor. My name is Pang Junwan, normometric AF220100. Now I will present this slide. This slide is talking that in order to design the simply support beam and continuous beam, we need to refer to structural layout of the first floor. This is because that we need to do our calculation from the strap to the beams and differentiate the two-way or one-way beam and the beam in the placement and the location in the building, and we need to know about the connection detail. Now this is our project, our structural layout of the first floor. In this slide, we need to know about the design parameter. The design parameter is sent of the all members in our group, so we can see that the material and the purpose and the specifications. But there is the one important thing is there are the two different sides of the steering we use, which is the 3 mm of the diameter steering for the simple support beams and the 4 mm diameter steering for the continuous beam. In this slide, I will present my design of the simple support beams. The beam selection I select is the beam 4A stroke D to C. That is the picture that I cropped from the structural layout. So we can see clearly there is a stats area in right hand of the beams. So that is the proof of the no strap area. So another strap is the two-way in the left hand side from the beams. The column is LY. The beam is the longer beam in compared to other beam in the same area. There are the two roller support in both ends of the beam. So we can assume that only have the vertical direction of the support. So the first step in design a simple support beam is we need to determine the size of the beam. After we calculate in the formula given, so it will show in the picture and in the slide, we can do and get the 150 mm of the width of the beam and the 300 to 20 mm of the height of the beam. And then we need to calculate the durability, fire bond and equipment based on the Eurocode, and we can get the C norm we use is the 35 mm. Now there is the important role to design a beam, which is the loading analysis. So there is a load from the action from strap A and only one strap because the another strap is the stack area. So there is no strap acting on the beams. So we can see the strap is the cast 3 based on the Eurocode, and we need to calculate the shear wave of the beam and total GK and total QK. So this is the calculation as shown below. Now moving on the second step, we need to apply the WD with the 1.35 DK plus 1.5 QK. So there is the design action we need to know, and there is the shear force diagram and the bending moment diagram. So after that, we need to calculate the main performance, which is the effective lift and the D and the design bending moment K. And so after we calculate the design bending moment is smaller than the K balance, so we can conclude that there is a compression balance moment is not required. So after that, we calculate the Z, X, and the area of the tension sphere. So we can get is the 331.47 mm squared. So we use the AS proof from the table in the Eurocode is 2H16. So that can prove our purpose. We use the tension, the diameter of the tension bar is 16 mm. And then we need to draw the link arrangement and calculate the X, which is the distance about the about the shear force resistance to the beams with the distance and the additional longitudinal reinforcement, and then we need to calculate the minimum length, and we can get that we use the link, the shearing is the H3 stroke 125. So there is the shear resistance of the minimum length in my design beam is the 10.94 kilonewtons. And the last step, we need to calculate the deflection and the cracking. So the formula that we use is follow the Eurocode design. So we can take, and the important thing, we need to calculate the bar spacing and the factor of the structural system K equal to 1.0. This is because it is the simple support beam. And then we use the equation 2 to calculate L per D, and L is smaller than the 7 meter. So the MF span equal to 1. So there is the simple support beam detailing. We can see that there is the two support, which is the B and the C, and we assume that there is the roller support, which is the one direction vertical acting force, the vertical acting support acting to the beam. We can calculate there is the detailing of the beam. There is the 2 of the diameter bar, and the diameter of the tension bar is equal to the 16 mm. So there is fulfill the requirement of the typical detailing of beam, which is the number of the reinforcements, diameter of the reinforcements, and the length of the top and bottom reinforcement. So now I will present the continuous bin that I designed in this project. The bin I select that is the bin B2 strap 1 to 3B. So there are the 3 straps acting on the bin, 2 straps acting on the bin from the upside view, and the 1 bigger strap acting on the bin from the bottom side. So we can see that all of the strap is the 2-way strap, and we can assume that all the support is the roller support. So same as the previous, we need to determine the size and side of the bin is different from the simple support bin. This is because that is the longer of the length of the bins, and calculate the durability of the fire burn equipment, and we can calculate we use and get the stand because XC1660 we use of the fire resistance. So the C norm we calculate, we get that is equal to 35 mm. So moving to the important part in this design of the continuous bin, is the loading analysis. So in order to do the analysis of the loading, we can get from the action upon the strap A, strap and B and C, and strap A is the same as the case 2, and the strap B is case 4, and strap C is the case 1. So the BVX we use because the strap is the longer span, so we need to get the BVX from the cable, and after that we calculate the shear wave of the bin and subtotal of the DK value, and we can get the total DK and total QK, and then we tabulate all of the result to easy for us to do the design and analysis. So there is the case 1 that we can get from the optimal bin to get the bending moment value and the shear force value. So there is the result that is shown in the slide. So we apply the optimum bin this website, and we can get all the both of the case, which is the case 2, case 3, to get the shear force value and the bending moment value. So there is the all that is shown in the slide, and the span 1 to 3 and strap 3 to B, we calculate the main reinforcement as usual. This is the calculate the effective lift and the bending moment, and the compression reinforcement is not required because the K we calculate is smaller than the K balance. So we calculate the Z and the area of the tension reinforcement, and then the minimum and the maximum reinforcement area we calculate AS min and AS max, which is the 0.04 times the width of the bin and the hash of the bins. So we can get that. So that is the result is okay because the AS minimum is smaller than the AS proof, and the AS proof is smaller than the AS max. And calculate the support 3. Support 3 we have the difference of the effective lift, and the bending moment we calculate the K, and as usual there is the model of the K balance, so the compression reinforcement is not required. We calculate the Z and the area of the tension reinforcement, so we use the 4H16 based on the area of the tension reinforcement, whether we calculate, and we use the AS proof, and then we calculate the shear reinforcement, which is the compressed capacity VRB max, and we substitute it when the delta equal to 22 and the delta equal to 45. So we can do all the calculation with the span 3 and 3B and the support of the 3. So we can calculate that the half floor 100 is equal to the span 1 to 3, and the support 3 is the half floor equal to the ceiling if we use is half floor dash 25, and the span 3 to 3B is the half floor 100, and the support 3B is the half floor then 200. Hence, the last step we need to calculate the cracking. The cracking in the limiting crack width W max is equal to 0.3 mm, which is the refer to the Eurocord, and the max allowable bar spacing we calculate, we get that is equal to the 135 mm. So we calculate the bar spacing for the support span 1/3 and the span 3/3. So that is the result that we'll show in the slide. Hence, there is the continuous bin detailing, so we can see that all the equipment of the detailing of bin we have fulfilled, which is the number of the reinforcement, diameter of the reinforcement, and the length of the top and bottom reinforcement. So there is the detailing of the bin because there is only have the tension area 3H60, and the above is the not have the reinforcement, and another is the 4H16, and the last is the 3H60 again. So there is the bin detail for my project of the design continuous bin detailing.